Routing basic text tasks over the internet incurs immediate friction. Every time a mobile app pings a remote language model for a simple data extraction, it burns bandwidth and racks up per token billing charges. Extracting structured data, like strict JSON, from a probabilistic cloud model requires extensive prompt engineering and fragile regular expression parsing. If the model adds a conversational preamble or drops a single bracket, the parser breaks and the application state fails. Apple addressed this bottleneck in iOS 26 with the Foundation Models framework, deploying a vertically integrated local solution running directly on the operating system. The framework eliminates structural instability by taking swift compile time macros and linking them directly into the autoregressive decoding phase of the device's local language model. Executing inference entirely on local silicon delivers two immediate operational advantages. Queries execute with 0-millisecond network latency, and user data never leaves the physical boundary of the device. Maximizing the potential of Edge AI requires abandoning the practice of treating models as external API wrappers. It requires treating generative intelligence as a native system component, governed by strict systems-level compiler integration. The iOS ecosystem relies on a specialized 3 billion parameter neural network. Executing a model of this scale on an edge device with a shared RAM architecture demands strict adherence to physical memory bounds. To fit within mobile constraints, the framework applies aggressive 2-bit quantization. 16-bit parameters physically compress down to 2-bit representations, reducing the footprint to 750 megabytes. Then, memory blocks physically merge, sharing key-value cache across sequences, decreasing memory overhead by 38%. These hardware optimizations serve as a mandatory prerequisite for local generation. Shrinking the physical footprint allows the device to hold the entire model in active memory without exhausting the system's thermal limits. Once the physical memory bounds are solved, the engineering challenge shifts entirely to controlling probabilistic token selection through precise software directives. At its core, an autoregressive generation cycle operates by calculating a probability distribution, or Logits, across an entire vocabulary to determine the most mathematically likely next token. The inherent looseness of unstructured text generation directly conflicts with the strict syntax requirements of type-safe data serialization. During the decoding phase, constraint sampling introduces a dynamic JSON schema overlay that actively scans the vocabulary. When the schema requires an integer, the overlay identifies all non-numeric tokens, and their probability bars instantly drop to mathematical negative infinity. Because their logits evaluate to negative infinity, the inference engine's selection of a syntax-violating token becomes mathematically impossible. This architectural shift removes the necessity for developers to write regular expression safety nets or complex retry loops to catch formatting errors. Intervening at the point of token selection ensures structural stability at generation, bypassing the latency of validating compiled strings post-generation. Translating these mathematical engine constraints into developer tooling requires a bridge. Swift macros provide that direct connection to the model's token sampler. This illustrates the generable macro. When applied to a Swift struct, the macro synthesizes a strict generation schema mapped directly from the source types. The macro automatically generates a custom initializer, allowing the application to decode structured outputs back into native Swift objects without intermediate JSON string parsing. To inject granular semantic logic, developers apply the guide macro. This provides property-level instructions directly to the generation engine. The guide macro enforces specific mathematical boundaries on the token selection. A developer can specify inclusive numeric bounds for an integer, or mandate exact array lengths to prevent runaway generation. The compiler translates these constraints and semantic descriptions into an expressive JSON schema, which is directly injected into the language model's system prompt. By utilizing declarative Swift macros, developers convert structural formatting from a runtime request into a compile time guarantee. Operating with structured types introduces the JSON streaming paradox. Appending raw, incomplete string deltas to a buffer breaks standard JSON decoders until the final token is generated, making real-time UI updates impossible. The framework resolves malformed data streams using snapshot streaming via the Stream Response API, preventing raw string exposure. This diagram reveals how the generable macro handles incomplete data. It synthesizes a partially generated structural mirror, actively transforming every individual property into an optional type wrapper. Declarative UI frameworks like SwiftUI bind directly to these optionals. Because the data type is valid even when empty, interface elements can animate instantly as individual properties populate from nil to a finalized state. Autoregressive models rely on temporal dependency. Tokens are generated sequentially from left to right, matching the exact chronological order of the Swift code declaration. Because of this sequence, architects must place UI critical fields like titles at the top of the struct. Complex dependent reasoning fields, like rationale summaries, must go at the bottom, granting the model access to the preceding tokens for context. Understanding the model's sequential generation vector allows developers to parallelize instantaneous UI rendering for the user, while heavier background reasoning continues uninterrupted. Despite these efficiencies, on-device processing executes within a strict hardware limit, a maximum combined context window of exactly 4,096 tokens. This equation defines the system's token consumption. The total available output capacity is cannibalized by the system instructions, the prompt, active tools, and the generated schema itself. Developers must protect the remaining output budget by minimizing schema complexity. Using concise property names like ID instead of System Asset Identifier directly preserves token space. To mitigate cold start latency, the framework exposes a pre-warm method. Calling this during idle states proactively loads weights and system instructions into the prompt cache, dropping first token response times under 150 milliseconds. The architecture must also explicitly handle two primary failure modes: local safety guardrail violations and context window exhaustion. In edge extraction tasks like optical character recognition, systems use a self-consistency loop. If the extracted data violates a mathematical invariant, the system permits exactly one reprompt, supplying the model with its previous error and requesting correction. Production architecture relies on a three-tier fallback pipeline. The system attempts the AI override first, degrades to a hybrid regular expression blend if confidence is low, and finally drops to pure deterministic parsing if the model fails. Robust edge applications treat a local language model as a participant with a heavily weighted vote, but never granted a veto over system reliability. Guided generation marks a definitive move away from manual string parsing toward compiler-enforced structured local generation. This flowchart illustrates the updated development pipeline. The iOS developer's role moves from writing fragile prompt engineering instructions to architecting strictly typed data contracts that govern the engine's behavior. This architecture provides critical security benefits. By structurally isolating static system instructions from the dynamic prompt builder, the system mitigates the risk of untrusted user inputs hijacking the session. Migrating intelligence to local silicon restructures app economics by permanently eliminating per-token API billing. A fully local architecture with zero network hops removes the unpredictable loading states that often degrade the user experience. By confining all generative data within the physical device boundary, the system provides a structural guarantee of user privacy. Building for the edge moves AI out of the realm of API integration and into the discipline of systems architecture, defined by compile time design.